So I'm very happy to speak here today. So what I do is theory of distributed and parallel programming. And I'm going to talk today about, as Mark said, about some gap between theory and practice. And I'll talk about a general gap, and then we'll go into some specific details. As the title suggests, the last part of the talk would be based on joint work with Dan Alistarh and Nir Shavit. But let me start with the big picture. Okay, so gaps between theory and practice. So we all know that in theory they don't exist, in practice they do. We can find them everywhere. In this talk I'll zoom in on concurrent programming, okay? So here's what we have. We have different types of systems that are parallel systems. You can have different type of architectures. You can have SMP or NUMA architectures. You can have different levels of caches, different memory access orderings. Basically, you run your parallel programs, and you want them to work correctly and fast. Okay. In theory, what we have is a model for how this works. So our model typically has several threads or processes. In this talk, they'll just be circles, colored circles. And they run an algorithm. And their algorithm tells them when to access the shared memory and how to access the shared memory. Okay. Now, here's the main difference between theory and practice. In theory, we want to have provable guarantees as to how fast your algorithm works. Okay? And I'm going to talk about how fast things work and not about correctness, though that is also a place where we have gaps. Okay? So we want to have provable guarantees. You know, this is the time each operation will take in this implementation of a certain data structure. Okay. So this is what we have in theory. In practice, what we do is we simply, we have our code, we have some guarantees that we can prove on it, but then eventually we go and we test it on a bunch of benchmarks, and we say, hey, this runs fast, this works really well, okay? And here's this gap between the two. So we want to be able to prove things, but we're proving them on theoretical model, okay, which many times does not represent faithfully what happens in practice. On the other hand, in practice, many times we don't understand what really are the underlying assumptions of what we code, okay? And really what I want to talk about is the goal of sort of bringing these two closer together. Now, I don't mean that, we should merge them. They should both exist, practice and the theory that gives us the underlying principles of what we do, but they should have a better dialogue, as I see it. So our theoretical models should better represent what happens in practice, and our understanding of what we do in practice should be more provable and more sort of with guarantees. Okay, so you know, this might all sound reasonable or not. Let me give you a specific example. Okay, so solving consensus. When I took my first distributed computing class, one of the first things that I learned was that if we want to solve consensus in an asynchronous system where faults can occur, and we want to do it deterministically, then we cannot. There is simply no solution. Now, for those who are not familiar with consensus, I'm not going to formally define things. This is true throughout the talk. But basically, the processes have some preferences or some inputs, and they want to agree on a common value, common output. Okay. So Fisher, Lynch, and Patterson showed that this is impossible. Okay. So this is a well-known impossibility result, really a classic and very fundamental result in the theory of distributed computing. And then Lampert proposed Paxos, which is a consensus protocol. And this protocol actually runs very well. I prepared an evidence for this, but now I actually have two because Alex just told us that they use Paxos in their infrastructure. So that's one evidence. And the other is this excerpt from Wikipedia, which you probably can't read, and that's on purpose, but just get an impression of the number of bullets here. So the subtitle of Wikipedia says that this is examples for production use of Paxos. Okay, so we have here products by Google, IBM, Microsoft, and so on. So everybody uses Paxos. So to me, this is a proof that Paxos works, and it works well. Okay, so how do these two settle in together? So how can it be that we cannot solve consensus, and yet we do? Okay, and the answer is simple. Fisher, Lynch, and Patterson's proof, what it does is it takes your proposed algorithm and it carefully builds an execution, so it carefully orders the different processes so that you can never reach agreement, okay? Now, here's the thing. Fisher, Lynch, and Patterson do not actually sit inside our machine, right? And our machine is not designed for the sole purpose of preventing us from reaching consensus. So in practice, when we run Paxos, it works, and it works pretty well, okay? So this long execution theoretically might occur, but the real chances for it to occur are very small, so it doesn't really happen. Okay, so we can have deterministic algorithm for solving a problem which is theoretically impossible. Okay, so that's the whole thing. We're assuming worst case in theory, but this worst case cannot really happen. Okay, Leeman and Ravin, this is a quote from an 81 paper of theirs. They said, they tried to explain what they use an adversary as a scheduler. So this would be the very long, bad execution. They're saying that the system has complex relations, and they're saying, well, it is also a very sound principle of system design to assume that the worst can happen. Now, I fully agree with this. If we want to have a system that is reliable, we need to have guarantees that take into account the worst case, okay? However, I propose not taking into account the theoretical worst case, but the worst case that could really happen. Okay? Now, this is a bit vague because this is what we need to be able to sort of model. What is the worst case that can really happen? I know what the worst case is. It's this very bad, long execution. But I want to be able to have a model in which this execution doesn't occur because it doesn't occur in practice. And in that model, which does faithfully represent what happens in the real world, I want to be able to analyze the worst case. Okay? So here's the answer for this gap between theory and practice. That theory assumes worst case, and practice it does not occur. And again, my goal is to bring these closer together. I want a different model for how these things work. And in that model, I want to prove guarantees with respect to the worst case. Okay. So this was just a toy example, and now I'll get into the example that I want to sort of analyze. And again, I promise not too many technical details. So suppose you want to have a concurrent queue, okay? So I'm going to describe the LockFree Queue of Michael and Scott. This is actually what you run when you use Java's concurrent link queue. The term LockFree means that someone always makes progress in the system. So if we had a lock, and the process that holds the lock, you know, they're sleeping, they're faulty, something happened to them, then the entire system is deadlocked, right? Because nobody can take the lock because it's used by someone and they're not coming, okay? When we have a lock-free queue, it means that if someone is stuck in traffic, still the other ones make progress. So someone always makes progress in the system. Okay, so I'll briefly describe the lock-free queue of Michael and Scott. So we have a head pointer to the head of the list and a tail to its end. There's actually a dummy object here, which I won't explain why it's there. In order to dequeue an item, you read the first item in the list, and then you try to change the head pointer to point to that item. Okay? You do that by a compare and swap operation, which is an atomic operation that changes the pointer. You know where it pointed before, and if it's still pointing there, it will point to your new object. Okay, so that's how you dequeue an object. If your compare and swap failed, it means that someone else already changed your pointer. Okay? So if it fails, you simply retry. Okay? And you simply repeat your operation until you succeed. Okay. If you want to enqueue an object, let's say I want to enqueue this purple object over here, I add it to the last item in the list by a compare and swap to that pointer, and then I do another compare and swap to the tail pointer to point to that item. If the cast failed, I retry. There's an asterisk here because the second cast, I don't really retry it. There is another mechanism that makes other processes cast that tail pointer for you. I won't go into these details, but the point that I want to make sure that, everyone understands is that you may need to retry the cast. Okay? So if it fails, you simply retry it. But the thing is that if your cast failed, it means that someone else's cast succeeded. Okay, so if you fail to change the pointer value, it means that someone else did a cast before you and they won the cast. When I say won the cast, I mean that it succeeded. Okay, so either you succeeded or your cast failed, but then someone else succeeded, and that's why someone always makes progress. Okay, that's why it's a lock-free queue. Okay, good. It's a lock-free queue, so someone always makes progress, but it's not a wait-free queue. So there could be starvation here. So here's an example of an in-queue operation that never completes. Okay, so you try to cast it to the green object, but before you manage to do that, someone else came in and cast the blue object. So you try again because your cast failed, but then someone is there before you again. Okay, and you can, of course, continue this as long as you want, and the in-queue operation never completes. Okay, so there's still progress going on in the system. There are new operations that keep completing, but not this particular one. And in practice, this is not what we want. We want to make sure that really all our operations on the object complete. Okay, otherwise, this will not be good enough. Okay, so this is called wait freedom, if every operation completes, if we could guarantee that. Okay. So here's a gap. We want wait-free algorithms because we want to make sure that all the operations complete. But in fact, most commercial code is lock-free, okay? As an example of Michael and Scott's queue. And the question is why? Okay, so we have some partial answer, and joint work with Petrank and Timnat, we show that in many cases, if you want to have a wait-free algorithm, you really need to use a very complex helping mechanism. I won't define these things, it's just for those who know what it is. The reason I wrote here that this is a theoretical answer is because this cannot possibly explain why we use Michael and Scott's queue. The reason we use it, the practical answer, is that it just works. And in fact, when you run it, most operations will complete. We will not have this bad adversary that keeps bringing in people in front of us to enqueue their objects. At some point, we will be able to enqueue our gray item in that example. Okay. So let's dig deeper into what happens here. So this adversary is a scheduler. The entity that I'm talking about is a scheduler. This guy just tells the processes which goes next. The blue takes a step, then the green takes a step, and so on. And my claim is that this is not an adversary that is there to prevent us from, from completing our enqueue operation on the concurrent queue. Okay, so there is no evil adversary sitting there. And Hurley and Shavit asked, what is the right model for the scheduler? And they coined the term a benevolent scheduler. The benevolent scheduler, it's not this angel scheduler that is trying to help us, be able to complete our operations on Michael and Scott's queue fast. It's just a schedule. It's supposed to be good for a variety of data structures, a variety of algorithms. It's not there and doing exactly something good for your particular algorithm. Okay, so basically, this is what we want, a model of, so a better model or a practical model of a schedule that really occurs in practice. So in a recent work with Alistarh and Shavit, we proposed a stochastic scheduler model. Now, before I get into the details and analyze this, just 2 or 3 minutes, I want to say loud and clear that I don't propose that the stochastic scheduler that randomly chooses the next step models a real schedule. So a real schedule is not just a random process that chooses which goes next, okay? But there are 2 important reasons to look into the model of a stochastic scheduler. One is that it provides sort of a proof of concept that if we have different models for our schedulers, then we can actually prove things that might have better flavor, might represent better what happens in practice. Okay? And the other is that it allows us to build a toolbox for analyzing concurrent programs under different schedulers as well. Okay? So this is why I want to look at this scheduler. Now, if we have this random scheduler, so this thing, just if you have 8 processes, just chooses each process with probably 1/8 to take the next step. Okay, it's a very simple, non-realistic model. In this model, lock-free is wait-free. Okay, So here's the thing. Suppose I have n processes, and I know that in t steps, if you get t steps, then you complete your operation. Okay? Now, the probability that the blue process gets t steps in a row, okay, is at least n to the minus t. Okay, so there is some positive probability that you get enough steps in a row, okay, so consecutive steps, so no one even took steps in between, in which case the blue will finish its operation, okay? This means that in expectation after n to the t steps, blue completed their operation, okay? This is what I call individual latency. So lock-free is wait-free. Everyone completes their operation in a finite number of steps, okay? Now, this is not very exciting because it cannot possibly explain why we would settle for lock-free, because n to the power of t is totally unacceptable. Okay, so there has to be a better explanation for this. Okay, so we dig deeper. Okay, and let's dig deeper into what happens in a certain family of algorithms. Just think of the Michael and Scott's queue. Okay, so processes can be in 3 different states. I'm assuming now even an easier algorithm where you just read the value of a pointer and try to cast it. Okay, and if you succeed, you're done. You're done. So you can either be about to read the object, the pointer, you can either be about to perform a cast that will fail, or either be about to perform a cast and win it. Okay, the initial state is this. Let's say we have 2 processes, so they're both about to read. If the blue takes a step, then purple is still about to read, and blue is about to perform a winning cast. Okay? And in general, we can have many states and transitions in between them. Okay, so this transition over here is the one I described earlier, and we have many transitions. With a stochastic schedule, the probability of each transition is 1 over n, in this case 1 over 2. But this can model any scheduler. Okay? Now, this is for 2 processes. You can imagine what happens if I have n processes in general. Okay? So this system is really hard to analyze, this Markov chain. What I want to analyze here is how long does it take me until blue wins a cast, until I'm in a state where blue performed a winning cast. Okay? So instead of analyzing this chain, what we do is observe that we have a symmetric structure here. Okay? So every time that every state that I have where blue is about to win or where blue just won the cast, I have another state that is sort of totally symmetric for purple. And I can take advantage of this and look at a smaller chain, okay, which I'll call the system chain, in which symmetric states will be considered as 1. I'm not going to formally define this, okay? And I'm going to use some theory of Markov chains and be able to show that if I analyze the green chain with only 5 states here, I can actually deduce what I want about the gray chain. Okay, which in general can be much larger, okay? And then we need a way to analyze the green chain. I'm not going to get into the details, but basically, every time that I find a winning state in the green chain, it balances as to which process actually won that winning state, okay? So this is the result we get. So Q and S here are parameters of a general algorithm. Again, you can think about them in this example as 1. In Michael and Scott's Q, they will be larger, but they will still be a small constant. Okay? So what we get is that someone makes progress, this is system latency, in order of something like square root of n. And each particular process makes progress in n times that value. Okay, so this is still on the theoretical side. This is asymptotic analysis. But it makes more sense, and it improves upon the analysis we had before. And it gives us these 2 new things. It gives us a new toolbox for analyzing the real schedule, what real scheduler might be, how a real scheduler might behave. And it gives us some intuition that we can prove things if we try to model a real scheduler better. So that's basically what I wanted to show you. The take-home message is that we're really looking for better mathematical models for practical systems. Now, this was a very sort of specific example, concurrent programming and progress conditions in concurrent programming. But you can think about this much more generally. You can think about correctness condition that you want to test. You can think about any other software, hardware, otherwhere that you want to be able to model correctly and prove things about. Okay, so basically, again, what I want to do is bring the theory and practice closer together to more faithfully represent what happens in practice. That's it. Thanks for your attention.